I have to start the recording. All right, so again, reminder of what's in 1.3. This is where we're bringing in these predicate ideas, which are these kind of function type things, if you will, where we're being able to say statements that rely on an actual input, and then you can determine whether it's true or false based on that input. And then whoa, that's scrolling like an idiot. There we go. We brought in the quantifiers. So we have the for all and there exists. So remember that we are able to now quantify statements and kind of change the values that we're allowing ourselves to plug in. Does it have to work for everything, or does it just have to work for at least one thing? So we did a little bit of that. And then, so remember these kind of common constructions. Remember that the for all is usually linked to implication, and the there exists is usually linked with and. I actually realized, so some people might not understand why it's and here and not an implication. So I want to talk about that super quick. So you might want to argue that you could say, well, there exists. So if I say some bears are fuzzy, you might want to say, well, there exists a bear. No, sorry, there exists an animal X such that if it's a bear, then it's fuzzy. You might want to say, okay, well, I can use an implication here as well. The reason we're not going to be able to do that is because the fact of the implication brings in this if factor. You know how implications are if then. So this is essentially saying there exists an animal such that if it's a bear, then it's fuzzy. But it kind of doesn't get across the point that there does exist this X such that it's a bear. Like once you have that if in there, it kind of gets rid of the actual punch of there exists a bear that is fuzzy. This is saying that there exists an X such that if it's a bear, but maybe it's not a bear, maybe no bears exist. That if kind of gets rid of that, kind of adds a lot of ambiguity there. So that's why we don't use implications with there exists, because we need to say that there does exist this X. And having that if statement in there doesn't quite pack that punch that we needed to have, if that makes any sense. So we did some of that, and then we talked about negating them. So we can also negate these quantifiers, and remember that we always want to make sure when we negate something that we always bring the negation as far inside as possible. So you don't want to leave it outside of a quantifier. You also don't want to leave it outside of a logical connective as well. So we left off with one last example for these types of ideas. Actually, two more examples, sorry. So let me unshare and reshare one more time, just in case. All right, so getting to one of these last few examples in 1.3. So we have the following predicates. The domain is all cars. So we're going to have that the predicate S of X is going to mean that X is a sports car, E of X means X is expensive, and A of XY means that X is safer than Y. So the first thing we're asked to do is to translate that thing into everyday English. So first, let's try to translate it kind of literally, and then maybe think of a better way to phrase it that actually sounds like modern English. So if I wanted to start translating this, well, let me just start from left to right. So I have that universal quantifier. So that's going to tell me for all X, but remember I should always state the context of that variable. So we're going to say, so this is the literal translation, literal. So the literal translation here would be for all cars X. So make sure to put the context in there. So for all cars X, then we have S of X, so that means X is a sports car. So for all cars X, if X is a sports car, sorry, because we do have this implication coming up. So if X is a sports car, then, and now we have there exists, I shouldn't have made the circle like that. There exists a Y, so then there exists a car Y such that E of Y, so Y is expensive, and a, y, comma, x. So remember, order matters here. So we'd have y is safer than x. So for all cars x, if x is a sports car, then there exists a car y such that y is expensive and y is safer than x. So that would kind of be the literal translation if you just kind of work from left to right. If we want to use more everyday language, which I can't spell correctly apparently, if we want to use more everyday language, we can probably say something like, for every sports car, there is an expensive car that is safer than it. That is safer than it. As always, I'm not a huge stickler for wording as long as it gets the point across. Usually, even when it comes to quizzes and exams, if you just want to use the literal, I'm usually pretty fine with that. I usually don't force you to make it sound better, as long as you get the idea of how to write it in English. So hopefully that makes sense. I'll wait a second to see if anything pops up in chat before we go to the next bit. Okay. I'll wait a few more seconds just in case someone's writing it down. Teaching to a screen is weird, guys, so if you ever need me to slow down or whatever, just let me know. All right. Okay. So this is still the same problem. So formally negate this statement in part A. So let me remind us of the statement that's in part A. Well, actually, just so that I don't run out of space, I'll just write it as we want to negate this entire thing. And this was the statement in part 1. So for all x, s of x implies there exists a y, e of y, and a of yx. Simplify your negation so that no quantifier and no connective lies within the scope of a negation, then translate your negation into everyday English. I thought I gave myself more space on this question, but apparently not. So I might need to squeeze it a little bit, but it'll be all right. So again, we don't just want to say negative all of that. We always want to make sure that the negation goes in as far as possible. Now I'm going to write this as if this were a proof. By that I mean I'm going to say each step that I use on the side. So also I'm going to take a side note really quick. So 1, 2, with all of the implication and equivalence rules, I know is a bit rough, and it's probably partially on me for not explaining it well enough. So I'm trying to find the time. It hasn't happened yet, but I'm trying to find the time to create a few hopefully short videos to try to clarify some of that stuff. And how we can use these rules to rewrite things. So hopefully I have that up in the next day or so for anyone to look over. But just remember that we just have these rules, and you can always have them next to you. You'll have them on quizzes, you'll have them on exams. And we're just looking to see which one of them fits in this situation and how can we rewrite what we have using that rule. So I'm going to kind of list the rules that we're going to use off to the side here to essentially rewrite this to bring that negation inside. So the first rule we're going to use is actually the negation. So we're going to use our universal negation. And if I can scroll up super quick, that's the thing that well, okay, maybe not. That's the thing that we're presented in this section. So this is the universal negation, an existential negation if we ever want to use it. So again, just to remind you, that essentially means that we bring the negation inside the quantifier and then just switch the quantifier. So that's essentially the first step we're going to do, is we're going to bring this negation essentially inside the quantifier but then switch the quantifier. So it's no longer a for all, it's a there exists, and then negation, sorry, and then the negation essentially just comes inside to the rest of it. So I gotta rewrite it all. And maybe I should have pulled up those rules in chat again. If you scroll up far enough, you'll find them. So the next thing we want to do is we still can't leave this negation outside here. We need to bring it inside. But we don't have a rule that tells us how to negate an implication. So we need to change this from an implication to something else first. And we have something that does this. So sorry, I should have said universal negation on 1. Should always list the steps that we do these on. So we do have a rule that takes care of that. It's our implication rule. And so we're going to use that on line 2. Okay. Sometimes. On line 2. And just a reminder that it essentially tells us that if we have P implies Q, that can become not P or Q. Okay, so that's the implication rule that we're going to use here. So this is going to become there exists an X, negation. And so then we're going to have not S of X or this entire back piece. So we're using that rule to be able to change from an implication to an or, because the point is that we couldn't bring that negation in as it was, so we needed to switch it over because now we have a rule that tells us what to do when we essentially distribute a negation. That's another thing. So your quizzes got graded. The answers are up on Blackboard. I tried to be as nice as possible with those first two. But anyway, there seemed to be some understandable confusion between two rules. So there's the distributive rule, which tells you essentially how to take care of something that looks like this, where you have essentially a statement on the outside that you want to distribute. And then there's rules to take care of essentially distributing a negation, but that's called De Morgan's. So a lot of people were saying that De Morgan's was distributive, and I kind of saw where you were coming from because we're kind of distributing a negation, but distributing the negation is technically called De Morgan's rule, De Morgan's law. So we use De Morgan's law here, and I usually just say it as De Morgan's. And essentially that tells us that when we bring a negation inside, we're going to negate both things. So here we're going to have not S of X, but then you also switch the logical connective. So this or becomes an and then we have the negation on the other piece as well. AYX. Dun, dun, dun. After that, if you ever have two negations by each other, if you will, you can get rid of them by using double negation. So double negation on 4 will allow us to take that not and essentially make it go away. So that'll just become S of X. Everything else will stay the same for now because we always do one step at a time. Makes them a little tedious, but so we use that double negation to get rid of that not in front of the S of X. And now our next problem is that we have this negation right here that's still lagging. Where's my little circle? Hello. There we go. So we have this negation here that is still on the outside of a quantifier. So we still need to keep going. It's still not far enough. So we still need to push this negation inside of that quantifier. So we'd have to use our existential negation now. So that's on line 5. So essentially everything else is going to stay the same except that last piece. So whenever we bring in the negation, we switch the quantifier. So this is going to turn into a for all y, not E of y and A of yx. We're still not done because now the negation is still in front of a logical connective. So that's still bad. So we need to push it in one more time, and then we'll be done. So we need to push this negation inside. Since it's an and not an implication, we know how to do that. Once again, if we want to kind of distribute that negation, if you will, that's going to be our De Morgan's law. So we're going to use De Morgan again on line 6. Everything's going to stay the same except that last piece. So when we use De Morgan's, we bring essentially the negation through, so it negates everything and switches the logical connective in the middle. So we switch that and to an or and negate both pieces. The only last thing we'll do is, since we started with an implication, if you start with an implication, you usually change it back to an implication at the end. But the only thing that we can change back into an implication, because again, our implication rule says P implies Q can become not P or Q. The only or we have is here. So we're going to be able to use this idea on that piece, where essentially not E of Y is, maybe I shouldn't write it like that, is going to be the P, and not A of YX is going to be the Q. But essentially we're starting with the or statement. So we're going to change that over into not P implies Q. So it's going to essentially turn into not E of Y. And then the Q is going to stay the same. So I'll leave that piece of red up there. But I'm running out of space, so I need to write a little more. So implication, to change it back into an implication. I'm not going to be able to write the English statement here, but that's okay. I'll just force it down a little bit. So this is going to become not E of Y implies not A Y of X. Another one. The very last thing is that we could use double negation to get rid of that not Y in front of the EY. So there exists an X, S of X, and for all Y, E of Y implies not A Y X. Whew. What's the difference between universal negation and existential negation? As the way I've been explaining them, almost nothing. So really the only difference is, what did you start with? Did you start with a universal, or did you start with an existential? That's where the name comes from. If you started with a universal, it's universal negation. If you started with an exponential, existential. It's an existential negation. But the idea behind both of them is bring the negation inside and switch the quantifier. But the name depends on kind of which which quantifier you were starting with. So at the heart of them, there's not much difference because they do the same idea, but the name difference just comes from which one you're starting with. So let me scroll back down to all this giant hoopla. So hopefully that somewhat made sense. Maybe it's still terrifying to most of you, but that's how we could do it. I will say, if it comes to like a quiz or an exam, what was I gonna do for this quiz? Okay. So on this quiz coming up on Thursday, I'm not gonna ask you to negate, but it's definitely something that could come up on the exam. You wouldn't be asked to negate something this long. You would probably ask to negate maybe something, this long. So it's only 5 steps instead of, 5 or 6 instead of 9. But this one would be good practice because it's longer and has lots of steps to keep track of. Now, this question we technically weren't done because it says then translate your negation into everyday English, but now I've run out of space, so I'm kind of gonna drop down here to write it. So let me, because I don't need that much space for number 6. So let me just rewrite this really quick. So say we want to translate this. Let me start with the literal. So as we move from left to right, so the first thing we encounter is that there exists. So there exists some car X. So there exists a car X such that. Now, the first logical connective we're going to come up to is an and, so I don't need an if yet. We do have an implication towards the back, but we're not there yet. So we don't need to keep track of an if. So there exists a car X such that X is a sports car, because that was what S of X was. X is a sports car. And for all cars Y, and this is where we start getting into the implication, so I got to be careful with my ifs. So for all cars Y, if Y is expensive, then Y is, my pen suddenly stopped working, hello. Then Y is not, because we have the negation, safer than X. You could say it is not the case that Y is safer than X. Again, I'm not a big stickler for wording as long as the point gets across. So that would kind of be our literal translation. If we wanted to try to say it in a bit more modern day, everyday English, we could probably say something like, there is a sports car that is at least as safe as every, because we need that for all to get in there somehow, expensive car. Expensive. So there exists a sports car, there is a sports car, such that it's at least as safe as every expensive car. Again, I usually don't care whether you take literal or everyday. If I'm quite honest, literal is easier to grade, but whatever floats your boat. All right, what is this notification? Oh, that, okay. All right, I'm not seeing any questions, so we'll hop to the last one. I'll give it a few more seconds. Okay. So negate the following statement. If he is tall, then he is a basketball player. Now, I also want to phrase this in terms of a quantifier. So we're going to say that this means for all X, where X is people. We're going to say for all X, and let's say he is tall is T and basketball player is B. So then if he is tall would imply he is a basketball player. So this would be our original statement that I can't spell. And if we want to negate this, now this would be something that's kind of fair game for negating because it's not quite as long. So again, I'll kind of present it in proof-like notation. So this is our given because that's what we want to negate. Well, that is what we're negating. The negation's there. As always, kind of your first step here when you have quantifiers is to use the whatever quantifier negation. So since we start with the universal, this will be universal negation. on step 1. So bring the negation inside the quantifier, switch the quantifier. That's a really gross looking there exists. A little better. T of x implies B of x. But again, we always essentially want to push this through. Am I missing a? I am. We always want to push this through as far as possible. We can't have it in front of a implication, but we also don't know how to deal with it when it's an implication, so we need to change it over to a different form, so we need to use our implication rule. So we essentially negate the hypothesis, if you will. So negate the hypothesis, and it becomes an or statement. Once you've switched it over, now we can handle essentially distributing that negation if you want to think about it that way. So that's our De Morgan's law on 3. De Morgan says you negate everything in there and switch the sign. So we have not T of x and not B of x. I'll get to that in a second, Sam. And then we can use double negation on that not in front of the T. And actually I misspoke before, so I'll clear that up as well. Oops. What made you use for all in the original statement? Good question. So remember that our for all, how do I want to do this without making it look like I'm saying implies? I'll do a little curvy thing. That our for all usually matches up with, and this is actually helpful to the other thing I have to say as well, usually matches up to implication, and there exists usually matches up to and. So here when I say if he is tall, then he is a basketball player, I'm not saying that there exists one person such that if he is tall, he is a basketball player. I'm kind of implying that out of everyone in existence, if they're tall, then he's a basketball player. Does that make any sense? So while the for all isn't stated explicitly in the beginning, it's kind of implied that this is going for all people in existence. If he is tall, then he is a basketball player. So I can kind of tack that onto the front and still have the same idea coming forward. It doesn't change the statement at all, really. It's still saying that in general, if he's tall, then he's a basketball player. Hopefully that made sense. But also I semi-misspoke earlier in this last one. What I said was, if you started with an implication, you should end with an implication. And that was, I misspoke. The reason in the last one that we changed over back to an implication, so I'm talking about back up here. Actually, I need to go back up farther because it's the step before that. Why did we change back to an implication here, but I'm not going to change back to an implication in example 6? And it goes back to this idea right here. If you have the universal quantifier, it should be with an implication. And if you have the existential quantifier, it should be with an and. So technically here we had an existential that was linking to this and here. And then we had a universal that we had to link back up to an implication. So that's why that piece got changed back into an implication. Whereas over here, well, and I guess it made sense anyway because we couldn't even use the implication rule in example 6. But that's kind of why we don't have to worry about it in example 6. Not only because we couldn't, because this is an and not an or, but because we have an existential, so it should be linked with a and not an or, if that makes sense. And not an implication, sorry. So this kind of relationship between the two is kind of important. If you have an implication, it kind of links up with its buddy for all. And if you have an and, it kind of links up with its buddy there exists. Questions, concerns on 1.3 before we go and catch the last bit of 1.4 that we need to cover? Okay. Okay. As always, if you think of something later, let me know. Why is that doing that? Okay, so I've got to unshare this and share 1.4. Come on. 1.4. So a reminder on 1.4, because again, we technically started this. This was our logic in mathematics. So that's where we started talking about all these different definitions for even, odd, parallel, divides. So you are going to want to really try to remember specifically even, odd, and divides are going to be the one that comes up a lot more in terms of my problems than WebAssign. Also, I don't think parallel turned up on your homework anyway, but the even, odd, and divides are the ones that I'm going to use more often. So you are kind of going to want to remember those definitions. You're also going to want to know what a prime number is. So remember that a prime is something that's only divisible by 1 in itself. And so then we talked about all the different types of ideas, axioms, theorems, proofs, claims, conjectures, all those wonderful definitions. And then we came to the idea of these counterexamples, where if you want to prove, in this case, we were talking about if we want to prove for all x, p of x is false, we just find one counterexample that makes not p of x true, because of the fact that there exists not p of x is the negation of for all x, p of x. So we did one example of that, and now we were left with the last kind of bits here. So we'll get through this, and then we'll still have plenty of time to start 1.5, which is good. Bring the chat back up. There we go. So we saw back in section 1.3 what we did a few days ago, not what we just did. We would have shown that the negation for their, for my words are breaking. The negation too for all x, p of x implies q of x is there exists p of x and not q of x. So that was shown in 1.3 on Thursday. This means that if we want to find a counterexample to something of the form for all x, p of x implies q of x, all we have to do is find one value that makes p of x true and q of x false, which would make not q of x true. So essentially, if we want to negate this, find a counterexample for this for all statement, what we can do is we can find something that makes the if statement true and the then statement false. These little dots all over the place. So say I want to find a counterexample to the statement, if p is prime, then p squared plus 3 is prime. So here I have some kind of p of x implies q of x. And again, since it's an implication, it does kind of come along with its buddy for all x. So that's why we can think of it as this type of statement that we wanted to look at. So if I want to negate this and I want to prove it false, so I want to find a counterexample. So to find a counterexample, so what did we just say we needed? Well, we needed the if statement to be true, so we need p is prime to be true. But then we want to find something that makes the then statement false, so we need the p squared plus 3 is prime to be false. So we need to find a number that is prime, but when you square it and add 3, it's not prime. This is going to fall out pretty quickly if we just start looking at primes, so let's just start looking at primes. Excuse me. The first prime we've got is 2, so let me try 2. So if I have my prime is 2, and 2 is prime, so that makes that true. Well, then p squared plus 3 would be 4 plus 3. Well, that's 7, but 7 is prime, so that doesn't help us at all. So it's not 2. What about 3? So 3 is prime, so that makes that first statement true. But then what about p squared plus 3? Well, that's 9 plus 3, which is 12, which is not prime, because it's divisible by 2, and 6. So our counterexample would be 3. Of course, there are most likely lots of other counterexamples. I believe absolutely, I want to say any odd prime would work. So 5, 25 plus 3 is 28, which is even, so that's not prime. I'm pretty sure the only prime that doesn't work for is 2. So essentially, any odd prime, I believe, would be a counterexample for that. So that's the other thing with these counterexamples. You might not come up with the same counterexample as somebody else, but as long as they both are counterexamples, it doesn't matter. So that's how we're going to essentially find counterexamples for these implication statements, is we're going to find something that makes the first part true, but the second part false. So say we want to assume that x and y, let me try to leave that one in there, mostly. So assume that x and y are real numbers, so absolutely any number you can think of, and x is greater than y. Is it always true that x squared is greater than y squared? So we're essentially saying we have this for all x. I'm going to write this very badly. If x is greater than y, so I'm no longer using actual good symbols, then x squared is greater than y squared. So I could, of course, make those into actual predicates and have the actual full symbols out. But this is essentially what we're looking at, is we have for all x, if x is greater than y, then x squared is greater than y squared. So what we want to look for is we want to look for something such that x is greater than y, but then we want to make the x squared is greater than y squared false. So we'd essentially want to look for x squared is less than y squared. Because just to be clear, we want x squared greater than y squared to be false. So are there any numbers that do that? Well, there's lots of them. So for instance, for example, what if we let x equal 0 and y equal -1/2? So 0 is greater than -1/2, that's true. But then if we square them, we get that 0 is that greater than 1/4. It's not. So this would be false. So one counterexample would be x equals 0 and y equals -1/2. Essentially, x equals 0 and y equals negative anything would work. You can also do things like x equals 1, y equals -2. Essentially, the negative piece here is going to be the real kind of kicker that helps you, because squaring a negative number becomes positive. But we found a number that made the first part, x is greater than y, true, but the second part, x squared is greater than y squared, false. So we have our counterexample. Huge note. Examples do not prove statements. So if you wanted to try to prove a statement and you just start listing examples and saying, yeah, it works for all these examples, we're good to go, that you can't do that, because it has to be true for absolutely anything. And, well, I should be careful. There are certain statements that you can prove by examples, but not pretty much none of the ones we're going to look at. If it has a very small domain, like say it was something that you needed to prove just for 1, 2, 3, and 4, well, then you can just show it works for 1, 2, 3, and 4 and call it a day. But if it's something in a similar situation to what we just looked at, we just found that that was not true. But say we were trying to prove something that looked like that. We just can't list off a bunch of examples because in here, in this case, it was all real numbers. You can't show that every real number works because you would never stop showing that they work because you can't do an example for every single real number. Just you don't have that kind of time or dedication. So examples don't prove statements, but a counterexample is enough to disprove a statement. So we can use examples to say that something's false. We can't use examples to say something's true. That's all I'm trying to get at there. That was the last piece of 1-4. Any questions on that? So we had an idea of counterexamples before, but now we have kind of a larger idea for these different types of, we kind of have this new statement type that we can find counterexamples for. Hold on 1 second. Oh, I don't know. It's most likely, yeah, this next one over here. No, you're fine. Sorry, teaching from home apparently means random people knock on your door. All right, so hopefully that would have given you time to ask about 1-4 if you had one. So we're gonna move on to 1-5. So I've got to pull that up really quick. So 1-5, where'd it go? There it is. So 1-5 is some other methods of proof. Now don't panic. It's not as similar to 1-2 as it seems like it's gonna be. Like right now you might see this and you're like, ah, crap, this is just another 1-2. It's a bit different. So don't panic just yet. We do need to talk about a couple other, zoom in, thank you. A couple other types of proof methods that we're going to be able to use here. And these ones are kind of going to be a bit more math centered as well, because this is a math class. But anyway, so we're going to discuss proof techniques. So most proofs in math are written in more of a paragraph form than what we've been using. We've kind of got this table kind of thing that we've been working with. And a lot of proofs in math are just kind of, you just kind of write. There's no list structure. It's just, you just write sentences of what follows from what. And so that's kind of the idea we're going to get out here. So a direct proof is kind of what we've already been doing. So for example, we proved in 1-3 on Thursday that the negation of that for all statement was this exist Q of X or not P of X. So we've switched around the P and the Q. I don't know why. Anyway. So we know that that negation of that for all is that exist statement, and this is kind of the proof for it, is that we're given the negation, you use your universal negation on step 1, and then you use the implication rule to change this from an implication to an or, so we used implication on 2, and then to essentially distribute the negative. I'm kind of going through this kind of quick because we kind of just looked at them. So distribute that negative, if you will, is our De Morgan's law. And then to get rid of that double negation in the front of the Q, we use double negation on 4. All this to just say, so if you kind of look at this, we're saying that line 2 follows from line 1, line 3 follows from line 2, so on and so forth. That's kind of the idea behind what we call a direct proof, is you essentially just say, here's this follows, this next thing follows, this next thing follows, until you're done. So you kind of just start at the beginning and just jump to something that follows from what you just said. So essentially, whoa, why do you do that? I swear, I'm not this technologically dumb, just freaks out sometimes. So the idea behind a direct proof is, say we wanted to prove some A implies C. So we wanted to start at A and get to C. Essentially, kind of what we've already been doing is we've been doing this idea of starting at A, getting to some B sub 1, getting to some next step B sub 2, and kind of continuing on for a while until we get to some other step that can finally lead to the result that we want, which is kind of exactly what this table right above is doing. Is we start with what we want, we eventually get to what we needed, but there were all these extra steps in the middle, and that's what these kind of B sub i's are representing right here. So these B sub i's would essentially be steps 2 through 4. But all I'm saying is that, again, direct proof, you start with what you want, and you just move to the next thing that you can say, well, this follows from that, and then from that I can get this, and then from that I can get this, and it just kind of walks itself out. So in 1.4, we also said that we need to sometimes take a look at axioms. And remember that axioms were the things that we essentially take to be true without proof. We just kind of take it for granted. And I believe I said on Thursday that axioms can kind of change depending on what you're looking at. If you're looking at geometry, you take a certain set of axioms. If you look at number theory and algebra, you take another set of axioms and all that jazz. So for the most part in this class, we're going to assume elementary facts about numbers, which you probably don't even think about. But here's oh my Lord, it happened again. Stop. So here's a formal statement of one of the axioms we're going to take for granted here. So if A and B are integers, so are A plus B and A times B. Like, that's something you probably don't even think about. Yeah, if you add two numbers together, you get another integer. Yeah, if you multiply them together, you get another integer. It's just something that you don't even think about. But that is technically something that we're taking to be true without proof. So that's going to be an axiom that we're going to use, and we are going to call on this axiom in some of the proofs that we're about to look at. We might get through two, maybe just one, depending on how long it takes to walk through. But we are going to refer back to this axiom. So whenever I say by axiom 1, this is what I'm talking about. I'm saying that if I have two integers and I either add them or multiply them, I get another integer. So say you want to do a direct proof. You want to write a direct proof. Well, here's kind of the steps that you're going to take to do that. The first thing you're going to do is you're going to assume the hypothesis is true. So that's kind of the if statement. So you're going to assume that part is true, and you're literally going to say, let the hypothesis be true. You're literally going to write that out. Then you're going to state the desired conclusion, which is essentially the then part. And you're going to state that as, we want to show conclusion. And again, you're literally going to write that out. We're going to use our definitions and other known results like our axiom to obtain the desired result. So we can only use things that we have defined or already shown to be true, or is an axiom and we're taking without proof. And then you're going to end by stating the desired conclusion. Usually you just kind of wrap it up as a therefore, blah, blah, blah. So I'm using that kind of a little bit. So this is essentially the steps we're going to take to do these proofs. So let's look at this first one here, and let me try to leave it so that kind of fits in there. And I'm also going to leave myself some space on the side, because just like with 1, 2, with those actual full proof ones, there's a lot of work that kind of happens on the side. Now with these first few ones that we walk through in these notes, if you're good at math, you can probably just see where it's going. But most of the time when you prove something, you do kind of have to jump over the side, do some scratch work, and then write the proof. So I'm going to do it that way, even though these somewhat walk themselves out, but I also shouldn't say that in case. Anyway, I'm just going to do the proof now. So say we want to prove that for all integers a, b, and c, if a divides b and a divides c, then a divides b plus c. So remember, I'm going to put it up here, that m divides n, so I'm going to use phrasing that's not in this problem, means that n equals k times m for some integer k. Now, also the thing about mathematical proofs is you have to be very careful to make sure you have all pieces. So there, for some integer k is actually an important piece of this definition. If k wasn't an integer, then it doesn't work. So if you're trying to prove that something divides something, you also have to show that that k value is actually an integer. All right, so let's try to look at this proof. So again, step one, assume the hypothesis. So you literally write, so the hypothesis, so we have if and then, so this piece is our hypothesis. So we're going to say, well, and we also need to assume that they're the integers that they are. So we're going to say let a, b, and c be integers, and assume, I'm going to write this on one line and kind of make my scratch work go down here, and assume a divides b and a divides c. So you literally state essentially the first part of that prove statement, everything before the and. You're going to let all of that be true. So let a, b, and c be integers and assume a divides b and a divides c. Let me just clear that up a little bit. Step two is to state the conclusion as we want to show. So we want to show that a divides b plus c. And now here's kind of the point where you'll usually come off to the side and start doing some work, so that you don't, just start babbling in your proof a little too much, because we want to make sure that the proof is very streamlined. So we don't want to kind of have that wishy-washy work in the middle of the proof. We want to do all the wishy-washy work off to the side and then state it in very logical, straightforward terms. So let's start using these actual definitions. So if a divides b, that means that b equals, let's say, k sub 1 times a. And I'm going to need that subscript because I'm talking about, I'm going to have more than one k floating around, so I need to subscript them. If you would rather use a different letter, that's perfectly fine as well. So I also need to say that a divides c. So I would say that this means that c equals k sub 2 times a. If you want to use k and j, whatever floats your boat. But that's kind of what I'm working with. And now I want to say this. So let me see what I would need to say for that to be true. Well, I would need b plus c to be equal to some k sub 3 times a. So that's what I'd kind of need. So let's see if I can take what I have and somehow get to what I need. And I'm going to have to scroll down a little. There we go. Well, let's see what b plus c would actually be. Well, if I write that in terms of the things that I just wrote out, so if b is equal to k sub 1 times a, and c is equal to k sub 2 plus, times a, k sub 2 times a, then those two things are equivalent, right? Well, they both have an a in them, so I can factor that a out. And I'm left with this. Well, okay, so also remember that this k sub 3 that I'm kind of trying to build up to needs to be an integer. But we have an axiom that says if k sub 1 and k sub 2 are integers, then adding them together gets us an integer. So why don't I just name this k sub 3? And then I have b plus c is a k sub 3 for some integer k sub 3. And that's exactly what I wanted. Cool. I've done it. I've done all my scratch work. I now know what I need. I just need to put it in the proof. Hopefully that made sense. So with these mathematical proofs, a lot of times it's come off to the side, use definitions to say what you have. Maybe you also want to take a look at what you want and try to manipulate what you have to get to what you want. And it's going to be a lot of algebra and that kind of jazz. But you just kind of manipulate it until you get what you want. And again, you do have to be kind of careful. We do need to make sure that this k sub 3 that we wanted is an integer, but since we have that axiom from beforehand, we can. So here's how we'd probably start writing this proof. So we're going to use our definitions and our axiom here. So we're going to say since A divides B and A divides C, there are integers k sub 1 and k sub 2 such that B equals k sub 1 times A and C equals k sub 2 times A. Now again, this is what I kind of meant by these ones. If you see where it's going, you can kind of just write the proof right away because my scratch work is essentially going to be exactly the proof. Sometimes the scratch work, you go off in a wrong direction and then you have to go back and try something else and you've got all this stuff that's actually not going to work. Whereas in this scratch work we just did, I don't want to say it fell out right away in case you didn't see it. But anyway, no, I'm going to stop talking and just start writing the proof. I really need to no one to shut up. So essentially, if we use the definition of divides to get these two statements, then we can say, well, B plus C is equal to A k sub 1. I wrote it the other way, so why don't I stay consistent? K sub 1 times A plus K sub 2 times A. And then you just show the algebra. So you can say, well, this does equal A K sub 1 plus K sub 2. And then you can say by axiom 1, K sub 1 plus K sub 2 is an integer. If you wanted to literally name it the new integer K sub 3, you can, but it's actually not exactly necessary. I just did it in the scratch work to prove that you can write it as K sub 3 if you want to. But we can just say that thing is an integer, so there is an integer such that it can be written A times that integer. Does that make sense? Hopefully. And that's essentially our proof. So at that point, we can say, therefore, A divides B plus C. And then you're done. That makes sense? I can't look out at all of your faces and tell, but I'll let that sink in for another minute or two, and then we'll do one more example, which is good because that'll take us up to our second type of proof for next time. But I'll let that sink in for another minute before I go on to the next example. So I'm not seeing any questions, so I'll move on to the next one. So say we want to prove that if A and B are odd integers, then A times B is also an odd integer. Okay. So again, first thing I should do is just state what I have and then state what I want. So the then is here. So we essentially need to take A and B are odd integers as our hypothesis. So we're going to say let A and B be odd integers. And then we want to show A times B is an odd integer. So again, at this point, if you're kind of confident, you can just start writing out the proof, but maybe you don't see how it's going to go here. So we're going to come off to the side and do some scratch work. So, well, the first thing is I said, let A and B be odd integers. Well, let me actually write out what that means in terms of our definition of odd. So if you remember the definition of odd, that means that, so n is odd if n equals 2k plus 1 for some integer. Okay, so we are going to need to check the integer piece again here. But that's a reminder of our definition. So if we write A and B in terms of being an odd integer, then we have that A is going to be equal to some 2k sub 1 plus 1. And B is going to be equal to some 2k sub 2 plus 1, where k sub 1 and k sub 2 are integers. Well, then I want to show that multiplying them together gets me an odd integer. So why don't I just take the stuff that I have, multiply them together, and see if I can somehow manipulate it to look like 2 times something plus 1. So if I have A times B, but that's going to be 2k sub 1 plus 1, 2k sub 2 plus 1. That's a 2. Doesn't look like it. Let me try to make that look more like a 2. There we go. Well, if I FOIL that out, hopefully y'all remember the first outer inner last distributing kind of technique, or as long as you distribute all of them to everything, whatever process you like, we would get 4 k sub 1, k sub 2, oh my lord, k sub 2, plus 2 k sub 1 plus 2 k sub 2 plus 1. Let me remind myself that I want some 2 k sub 3 plus 1. So I want to try to be able to manipulate this into something that looks like 2 times something plus 1. Well, hey, look, I got plus 1 right there, so I probably shouldn't touch that.
I have a question.
So, yeah.
Why are we using 2 and plus 1?
Right, so do I still have, let me go back to, it's on a different page, so I've got a, where's 1, 4? So we've got a, this is, oh no, this is kind of coming back to 1, 4 really quick. In our many definitions provided in 1, 4, we were told that an integer is odd if it can be written as 2z plus 1 for some integer z, and I'm just choosing to use k now because I feel like it. So if we're saying for this problem that a and b are odd, then I'm able to write them as 2 times something plus 1. And I'm using k sub 1 and k sub 2 to just represent those things that would be, I don't know what they are, but they're something. And since I'm told that a and b are odd, I can write it like that. Does that make sense?
Yeah.
Hooray. So it's essentially, yeah, going back to that definition of odd and using it to write the things that we're told are odd. We're told that a and b are odd. So if they are odd, I must be able to write them as some 2 times something plus 1. So now, so again, I'm trying to work up to, if I want their multiplication to be equal to some 2 times something plus 1. Well, I have the plus 1 already floating around, so I don't want to do anything to that. But, well, let me look at everything that I have left. Well, everything that I have left then, besides that plus 1 that I don't want to touch, is divisible by 2, because we have a 4 and then 2's. So I can factor a 2 out of all of those pieces. Well, if I factor a 2 out, so 2 k sub 1, k sub 2, plus k sub 1 plus k sub 2, plus 1. So that, again, that plus 1 did not get touched. It stayed. And I just factored a plus, I factored out a 2 out of everything else. Well, now let me take a look at what I have here, because if I can say that that's an integer, then I'm good to go, because again, it has to be an integer. But I have a multiplication of things, 2 times k1 times k2. Axiom 1 tells me if I multiply integers together, I get integers. So that first thing is an integer. And then what I'm left with is a sum. Well, axiom 1 tells me if I have a sum of integers, it's also an integer. So axiom 1 gets us that this is an integer. And I could rename it k sub 3 if I wanted to, which then does show me that if I multiply these two things together, I do get some 2 times something plus 1, which makes it odd by definition. So all that scratch work is now essentially going to be exactly what we want to write in the proof. Again, this one, the scratch work, well, I know how I'm supposed to do it, so maybe that's half the problem, but sometimes you'll have stuff in your scratch work that you don't need. But in this case, everything in that scratch work is essentially something we're going to want to say. So now we got to start using that scratch work and essentially just writing it in proof-ish language. So we have since A and B are integers, are odd integers, I should say, because that's the kicker. There are integers k sub 1 and k sub 2 such that A equals 2k sub 1 plus 1 and B equals 2k sub 2 plus 1. Again, that's just by our definition of odd. And then we can say so A times B, and then essentially just show them the math that we just did. So 2k sub 1 plus 1 times 2k sub 2 plus 1. FOIL that out. So again, if you can see where these are going right away and you don't want to do the scratch work off to the side, that's fine. The scratch work isn't required. But usually it does kind of help because sometimes you might not see right away how you want to do it. So then we wanted to factor out the 2. But leave the 1 on the outside because we were trying to build to 2 times something plus 1. I never know where to put periods when we're talking about math. I'm just not going to include them and be a terrible English person. And then we have by axiom 1, 2k sub 1, k sub 2 is an integer. Stopped working again. Because again, that axiom is telling us if we have integers, if we multiply them together or add them together, we have an integer. So we have a bunch of integers multiplied together. So that part is an integer. And therefore, the 2k sub 1, k sub 2 plus k sub 1 plus k sub 2 is an integer. So again, that is an important piece of this. We need to prove that it is an integer that is allowing this to happen. But then we have all of the steps written out. We essentially have that A times B is written as 2 times something plus 1. So it is in the correct setup for an odd number. So if you literally wanted to take an extra sentence and say, so therefore A times B equals 2k sub 3 plus 1, if you wanted to define it as a different integer, that's fine. But essentially, once you have the setup, you can just jump to the therefore. Once you have it all there, you can just say therefore A times B is an odd integer. And so those were 2 examples of direct proofs again, and essentially, again, the direct proof is just saying that essentially one statement just follows from the other, the one before it. Sometimes you have to come off to the side and do some scratch work to see what work you actually want to use. Again, if you can see it right away, you can just jump straight to the proof. But most of the time when proofs are written, you only see the result and you don't see all the painstakingly terrible work that was done off to the side. So don't feel bad if you have to come off to the side and do some work. That's how proofs work. But that's what we're gonna do. We're gonna stop there because we've only got 4 minutes and that's not enough to get in the next part. So we're gonna stop 1.5. Let me write in chat what you'll want to look over for your quiz. Let me remind myself what I want you to look over for your quiz. So quiz. It's on 1.3 and 1.4, so this 1.5 stuff is not going to be on the quiz yet. What you'll want to look at is predicates. So kind of like the beginning of 1.3 where we talk about like P of X is X is even. So P of 7 is false. Essentially where we bring in these predicates and then we can plug in values and say whether or not they're true or false. You're going to want to know how to do that. You're going to want to know how to translate predicate logic into English. So we did do a little bit of that today. We had already talked about it on Thursday, but we did another example of it today. And then from 1.4, you'll want that idea of counterexamples. So you'll want to remember what you need to find a counterexample. So we had those kind of two situations for counterexamples. If it's just a for all x p of x, or the other situation where it's for all x p of x implies q of x. So you'll want to remember how to find counterexamples in both situations. So that's in chat if you need it. If you have questions, feel free to stick around for a little bit. I have a class in a little bit, but I've got a little bit of time if you got questions. Otherwise, have a good day, and I will see you on Thursday.